way up to the top. So I want to get started with the lecture today. We're going to have basically two sections. The first section, we're going to just talk about expressions, values, types, and precedence, just how values are managed in Python. For those of you who are familiar with languages, you probably have a good idea for this. For others of you, maybe this is your first introduction, and we'll kind of ease you into, the idea of a written one on paper and how that's represented in the computer and what we can do with it. And we'll talk a little bit about a couple of different types we have in the computer or in the Python and operate precedence and why you have to be careful about different operations. Second half of the lecture, we're going to talk about variables in memory. I want to show you, now we're going to move from concrete numbers into how we store numbers, how, the same way your calculator kind of stores numbers, and how that works in Python and how to write a good Python expression. I don't think we're going to have, that's a lot of stuff. It doesn't sound like that much, but it's enough to keep us busy, and we will try to kind of get through all of that. Before we do, though, let's just talk a little bit about how this course is organized. We are giving you lecture notes. If you go to computer science, right, you come down here. Oops, that was code written in class. I'll get to that in a second. If you come down into lecture notes, right, we have lecture notes here. If you go to the discussion or if you go to Submittee, we have this course materials section. We have your labs are here. We have lecture notes here, right? These are PDFs of the lecture notes. So you're getting lecture notes. We'll try to do this at least 24 hours in advance. I can't promise that every time because, well, there's a lot of moving parts for this. But we try to get them out to you at least 24 hours in advance. Hopefully we will be able to stick with that. These are the same notes that I'm going to teach. It's going to cover most of the material you're going to need. It's going to cover all the material you're going to need. If you have your textbook, we'll try to give you little notes like this material is covered in Chapter 2. So if you want to read in more depth or you want to try some additional exercises, you can get to them there. If you get a chance to read the notes ahead of time, that's great because we can come in here and we can focus on the examples. We can focus on doing more deep dive on some stuff, or for giving you a better intuition for it. So we do recommend you try to read the notes and read through the examples before class, and then we'll use the class time to give you a better understanding of the material. Just take notes on your paper, take notes in a notebook, type them into a notepad or something if you want, so that you can remember what it is we're talking about on the notes. I prefer to do it right on the note sheet itself. I do that for myself when I'm getting ready to give you a lecture. So just keep notes for yourself. And then either ask questions about stuff that you're confused about or research it on your own. If you have the book, look at the book, research it online, etc. All these are good ways to get yourself a better understanding or a deeper understanding. As we go through the class, in particular, when we get into some of the later sections, we'll have long pieces of code, kind of like the triple doubles piece of code that we had in the last lecture. For something like that, we will have, I'm in the wrong window. There we go. Right? For stuff like that, for pinned to a specific lecture, we will give you some things that are long. So don't worry about typing things into your browser or into your Spider as you go along. It's on the sheet, but we'll also give you the code in a separate little repository. Shorter things, like the hello world we did, we'll kind of expect you to type in yourself, but you'll still get the exact text that we're using in the lab notes. So don't worry about those too much either. What you really want to take note of is what the output's supposed to look like so that you know whether you have it in there correctly or not. All right, any questions on that? Let me just pop over here for a second. Yes, I do. And we will get to that when we have a homework due. We're not going to. Yeah. No. Okay. Yeah, don't worry about your assignments until we tell you. If you go to the detailed schedule, you'll see when they're due. You will have at least a week before anything is due to work on it, or before our homework is due to work on it. The lecture exercises are much shorter. You'll have 24 hours for those, but we will tell you. You're not missing anything. We haven't. We're not trying to trick you. All right. So let's go back to Python as a calculator. I got to tell you, I'm not really all that happy with this. Not really happy with this WebEx. Anyway, so you guys have done calculators, right? You've got these little guys, right? I bought this back in, I think, 1986. Best calculator I ever bought. No batteries. Little solar panel in there, and it'll convert between hex and decimal and binary and trinary and octal and everything. So, by the way, the YouTube playlist is Professor Uzma's lectures from a previous semester. So it should be about the same as this, from, again, a previous iteration of this course. Since we had them available, we made them available to you. The ones that I'm posting are these lectures. I'm hoping to get a chance to edit some of them, but right now they are just plain, whatever I was able to generate. But you can use your Spider, for example, as a calculator. And we talked last class, this is a file editor, this is a console, and what we found out was that when we press the little green button, things that are here, like things that are here get executed in this window down here, and you see the output. But it's not always necessary to go between a file and your console. In fact, what we can do instead is we can actually type things into the console without ever putting it into a file first. And by the way, this works the same way in your terminal window. So if you come down here into a terminal window and you type in something like Python, right? Now you're actually in a Python prompt, and you can do something like, I don't know, print, if you can spell, right? And essentially this is the same thing you're doing when we're typing into the console here in Spider. So let's just run through a couple of things. What did I say we would do? I'm not going to do all of these because they get a little bit derivative after a while. But let's just do, we know that the area of a circle is pi times r squared, where r is the radius. So let's say we have a circle of radius 5, and we'll use 3.14159 as the approximation of pi. So we have pi times the radius 5, and we want to square it. Okay? Or maybe we want to know the number of minutes in a year. Well, there's 60 minutes in an hour, there's 24 hours in a day, and there are 365 days in a year. So we have 525,600 minutes in a year. If we want to know seconds in a year, well, then we need 60 seconds per minute times 60 minutes per hour, 24 hours a day, 365 days a year. And if we want, we can even add in a leap year. So that would be another day times 60 minutes times 60 seconds, right? So hopefully that's about right. I think that looks good. There's always the possibility I mess something up. But so we have this ability to just enter mathematical formulas, and and get results back. So let's look at these a little bit. Now let's do one more. Let's do the volume of the Earth in cubic kilometers. Well, you guys probably know off the top of your head that the radius of the Earth, at least at the equator, is approximately 6,378 kilometers. Right, so 6,378 kilometers. That's our radius. So we want to square that, and then we want to multiply that times pi. So we'll just use 3.14159 for pi. And, what is that? 127,796,375 and change cubic. Oops, wait a minute. That would be, yeah. All right. The volume of the Earth would be 4/3 pi r cubed. Right? So there's the radius cubed times pi, 3.14159 times 4 divided by 3. Okay, that's better. All right, so that should be the if I got that right, 4/3 pi r cubed. Yeah, if I got that right, that should be the volume of the Earth in cubic kilometers. Yeah, the hashtag was used to comment. Let's see, what else? Do we have anything down here? We'll get to some of this going forward, so I'm not going to worry about it too much right now. All right, so that's just a little bit of using Python as a calculator. So let's talk about a few things. The first thing I want to talk about, and by the way, I'm looking over here because that's where I have my notes, and when I can't see my notes, I need to look at my notes. The first thing I want to talk about is different representations. This value looks a lot different than this value, at least to me. Maybe it does to you as well. And let's talk about what these different values are. So when we're talking about values such as the volume of Earth, where we have this kind of partial values, we're talking about whole numbers, right? So you want to think of that kind of think of that kind of like you have a measuring cup, you have some purple fluid, and you can pour the fluid into the measuring cup, and right now I have one whole cup and about a half and then maybe an eighth, right? So I've got one whole cup plus some addition. This is a floating point number, right? You have something that looks on our spider like this. Oops. Like this, right? We have a whole part. That's the number of whole things we have. We have a decimal point, right? And then fractional part. And you guys should be good with this, right? I mean, this is just the real numbers. But they're different from, for example, my golf balls. Right? If I take my golf balls, well, I got a tin of golf balls that I found in the garage. I've got 4 in there. I've got 5 in there. I've got 6 in there, 7, 8. Right? I can't divide these up. Well, I could, but I need an axe or something, maybe a hydraulic press. These are integers, right? These are whole numbers, counting numbers, and they're different representations in Python. And in general, well, these represent what we call types. This is the int type, right? And our measuring cup of water is a float type. And they represent two different abstractions of things we can do in Python. So, come in here a second. When we talk about a type, there's two things that comprise it. One is the data, right? So golf ball. And the other is the operations that are allowed on it. And both whole numbers and integers have all of the mathematical operations that you would expect defined on them, right? So we have plus, minus, star, slash, exponentiation. We also have a couple that you may not be familiar with. Double slash is whole number division, and percent is remainder, right? So when you're talking about, particularly about integers, right? Let's say you want to find the number of seconds in, or the number of minutes in 3,750 seconds. Well, you know, if you divide by 60, right? 60 seconds in a minute, you get 62.5. That's not really what you want. You want the whole number of minutes. That would be 3,750 integer divided by 60, right? So if this is a number of seconds, that says we have 62 whole minutes, and we have a remainder, right, of 30 additional seconds to go, right? So whole number calculations, integer calculations are used for integer numbers, and then we have the same kind of values set up. Oops, you know what? I didn't switch to my spider. That's why this isn't looking right. Okay, you know, so if we have 3,750 seconds, we divide by 60, we get 62.5. Dividing any two numbers gives us a floating point with a decimal, right? So this converts between two integers. 3750 and 60 are both integers, and gives us a float. Whereas if we take an integer and do a slash slash, that's an integer divide, it gives us just the whole number of 60s that appear. And then the modulo function gives us whatever's remaining. So if we take and we say 62 times 60 plus 30, right, we should get back to our original number. This is number of seconds in a minute times the number of minutes, right, the 62, and the number of seconds that we have hanging out just left over there. All right? Float and int are the two initial types we're going to talk about. We'll also talk a little bit about strings, but only in the context of printing out our values. We pop back to presenting slides. One interesting thing about the modulo function and the integer divide is seeing how they work with positive and negative numbers. Integers can be essentially minus infinity, effectively minus infinity to plus infinity. We run out of space eventually in there, but they can get very big and very small, very negative. But because of that, both the modulo and the integer divide have to work on any integer. So when you start mixing positive and negative values, that gets kind of interesting. We're going to leave this as kind of an exercise for you because it's a fun way to explore. But see if you can figure out how modulo and percent work on positive and negative numbers. Okay. We talked about all of this. We talked about our operators, plus, minus, star, slash, exponentiation. If you want to see what type something is, you can always use the type function. So we can go type 62 will tell us that's an integer. Type 62.5 will tell us it's a float. Type 3750 divided by 60 will tell us that's a float. Right? Anytime we divide, we're going to get a float, even if we divide by 1. Right? But if we start doing modulos or integer divides or the modulo or remainder function, those come back as ints. Oh, man, I hate that. Thank you. All right, so you can use the type function, right? I'll go back through and of course now there we go. So if 62 is an integer, 3750 remainder or modulo 60 is an integer. Integer divide gives you an integer. Regular divide, even if it's by a 1, gives you a float. And something like 62 point or 62.0 are also floats. Okay? Now the representation matters because of the way they're stored. Integers are stored in a way that allows us to have essentially arbitrarily long integers. Floats are stored in a finite amount of memory, so there are limits to how much precision we can actually give you on a float. So for example, if we look at something like 2/3, right? The floating point representation of 2/3 is 0.6 ad infinitum. This is about how many bits we have, right? So that's the limits of our representation for a floating point 2/3. But now we can do something like 1 2/3, which is 5/3. And what happened to the 6 at the end? Or what about 8/3, 2 and 2/3? Right, now we've got a 5. Floating point numbers have a finite precision. We can't store all the data, right? Especially for something like 2/3 that's a repeating decimal. So what you find out is that these last couple of bits may not be exact. And it gets harder as you kind of work through. What if we did something like 1 plus 2/3? Right? That's the same as 5/3, but it gives us a different representation. So the point here is that floating point precision, floating point arithmetic is not exact. And when you start dealing with floating point arithmetic, if you're doing some of our tests for Booleans, if you're expecting an exact value, even on something as simple as 5/3 or 1 plus 2/3, you're going to start getting different answers just because of the way the math is carried out and the propagation of significant digits or of bits in your calculations. All right? To mute the chat, all you have to do is there should be a little X up in the corner. If you just hit that, or if you go into down at the bottom of your bar and click on the closed chat, you can get rid of that. Okay? Now to the precedence. Well, I guess I'll do one more thing here. Let's see how we're doing for time. We are okay. That is not always the case. All right. I've been saying a couple of times that integers allow you to have essentially arbitrary precision or arbitrary numbers of digits. So let's just start a little experiment. 1 times 1 raised to the first power is, and here I would expect you to shout out 1. So I'll just do it for you. And now let's do 2. Right, this is 2 to the 4th power. Right, 16. These get big fast. All right. Right, getting a little bigger. Can anybody do 4 without typing it in? No. And we can go on, which, by the way, if you look at other languages, like particularly compiled languages like C and C++, you can't do this. And that's because integers are also held in a fixed size piece of memory. Python is not holding it in a fixed size piece of memory, and it just allows you to get funky. Of course, if we do something like divided by 1, right? Now we've generated a value that is too large to be contained in a float, and the computer just kind of barfs on you. All right, sure. So no, it's not random. It actually depends. It is predictable, but you have to know the internals of how the calculation is being done. So it can look random to us from the outside, and the problem is that when you're doing complex calculations, figuring out how that flows through is very difficult. So what the point we want you to take from there is, just because it's giving you what is that, 5, 10, like 15 digits past to the right of the decimal, doesn't mean you have 15 digits of accuracy. Okay, so it's a deterministic. It's based on how on the precedence, the order of operations like this. This is different from that because we calculate the 2/3 first. Oops. That one came out right. Okay. I guess it was 5/3 was the one I was. It's because of the way that the registers in the chip work. We'd have to go into the algorithms for computing division. It's not worth it at this point. But it is deterministic. It's just for any sufficiently complicated computation, you're not going to know exactly what those last few bits are going to be. So you have to be careful. It doesn't have to be this repeating string either. It could be that 1 comes out to be 0.9999999, something like that. Okay, does that kind of answer your question? You'll learn more. Yeah, you'll learn more about this when you get down into assembler. And what is it? Is it still cold? What's the computer organization? Computer architecture, maybe. Whenever you're doing MIPS, you'll learn how these algorithms are actually implemented. Okay. Let's see. Where am I? Back to presenting slides. All right. So, the important thing to note is that integers don't have decimal points. They're whole numbers. Anytime you do a divide, you end up with a float. If you do an operation between a float and an integer, you end up with a float, right? If we go 1 plus 1 point, right? That is a float. Anytime you divide, you end up with a float. There are ways to cast from between floats and integers, so you can choose that representation. We'll get into those in a little bit in a couple of lectures. But these are the important things to take from this lesson here. Just don't be surprised when weird things start happening. They're all explainable. If we go now and look at the next step, we had PEMBAS in one of the questions. And that's exactly right. What we need to be careful of is, well, for example, let's look at converting Fahrenheit to Celsius, right? The formula for converting Fahrenheit to Celsius is the value in Fahrenheit minus 32 degrees, right? That gets rid of the 32-0 issue for freezing, right? So the number in Fahrenheit minus 32 times 5/9. Well, if we're a 45-degree day in Troy, which is coming up, if you guys are not in Troy, congratulations. 45 will seem very warm in a little bit, but really it's a end of October, beginning of November kind of temperature. Not bone chilling, but fairly cool. However, if we convert that to Celsius, we end up with something that looks like, a very nice, mild summer day as opposed to a mild fall day. And if, in fact, we do this in the reverse order, right? If we take 27 degrees Celsius and multiply that by 9/5 and then add 32, well, that's actually an 80.6 degree day. So these two numbers don't really match, right? 45 is not 80.6. And the reason we're having a problem here is because the computer has some very fixed rules for how it evaluates an expression like this. And it's all by your PEMDAS, right? This is something you learned in math a long time ago and probably forgot, but maybe not. If you didn't, good, you won't have to learn it again. If you did, what PEMDAS basically says is it gives an order for evaluating operations, right? So we start off, and this is, by the way, this is not only within Python. This is fairly consistent with within all computer languages. The first thing it does is it evaluates parentheses, right? That allows us to come into our spider, for example, and correct our initial issue, right? We can put in parentheses, and then parentheses become the highest precedence. We now calculate 45 minus 32 first, and we find out that 45 degrees Fahrenheit is closer to 7 degrees Celsius than it is to 27 degrees Celsius. So parentheses are at the upper level. The next thing down is exponentiation. And the weird thing about exponentiation is it is evaluated from right to left, which is the opposite of everything else. But it does map nicely into how you write exponents, 2 to the 2 to the 2. But what that means is if we have something like 3 to the 2 to the 3, is this? Thank you. Boy, I hate this. It should automatically move. I think I can set that up. That'll be the next thing I work on. I worked on volume and stuff today. So if we have something like 3 raised to the second power, raised to the third power, the question is this 9 cubed, right, which would be, 729? Or is this 3 to the 9th, which is not 729? So is this equivalent to that? Or is it equivalent to that? And because it's evaluated from right to left, instead of left to right, it's actually equivalent to this. You take the first one you see coming in this direction, apply it to get 2 cubed, which is 8, and then you apply this one, so that's 3 raised to the 8 power. Okay, that's different than for example, 2 times 3 times 4, but actually that doesn't matter anyway because of the associative properties of math. But it still is evaluated in that order. All right. The rest of the precedence rules should be familiar to you, I hope. Parentheses, exponentiation, right to left, unary negation, right? So that's, 7 plus minus 7. Right? This unary negation is applied right after exponentiation. And then you have your multiplicative and divisive operators, multiplication. I did that again, didn't I? Okay. 7 plus negative 7 comes out to be 0. That minus 7 is our unary minus. I've got to set up one more scene, I think, that has both of those in there. All right. So after the negation, then we have multiplication, division, integer division, and the remainder operator, also called modulo. if you're going to be listening to me, I have a hard time saying the remainder operator. I learned this as modulo way long ago. So learn modulo. It'll make it easier to understand me. It is the modulo operator, but it does do remainder. And then after that, only after we've done all of these do plus and minus actually come into play, which can be a little confusing when we have the negation, the unary minus, having this high precedence, and the arithmetic minus having a much lower precedent. All right, I'm going to give you just a couple of minutes to go through and look at some of these practice problems. Just see if you can kind of figure out what types these values are, how the Python interpreter would interpret these operators, and then, this ought to be fairly easy to you. All of these are pretty easy to self-check. One thing you can keep in mind is that if you're in Spider and you want to know what type an operator is, you can do type 7 divided by 32 plus 1, right? And that'll tell us that that's of type float. So you can check yourself pretty easy. Just go through and take a quick look at those. These are the types of things that could end up being on a test, especially early in the semester when we have we don't have a lot of stuff to test you on. So I'm going to give you, I don't know, like let's say my clock says 3:19. I'll give you till 3:21. You can always go back and do these later. Sure. So the left to right refers to evaluating the expression. So they have equal precedence, and what you would do is you would go, right, if we have 7 times 3, that's not a 7, that's an ampersand. 7 times 3 / 4 minus 9, and that's not a minus either. So I suffer from FFS, which is fat finger syndrome. Sometimes my fingers get too heavy and they land on the shift keys, and sometimes I hit one key off. I don't really have FFS, but it's a good excuse. So if we have an expression like this, what left to right means is that star, slash, and double slash, and percent all have the same precedence. So we start at this end of the equation and we do the first one we come up with first. So the first thing we would do is this, and then we would see the 4. So we would do this, and then the minus is at a whole different level of precedence. Does that make sense? What this affects more than, in absolute precision, right? You have this associativity rule that says in math, in infinite precision, it doesn't matter what order you do these in, right? The problem is we're not using infinite precision. So sometimes the order does matter. So it's important to know left to right or right to left. Okay? It's too hard to explain why right now, but we'll get into that in another lecture when we're talking about simulation. I hope. If not, you'll get into it in operating systems or something. Okay, and I talked away your entire little break. We're trying to keep you guys engaged. I don't know if it's working or not, but hopefully. All right, let's go back to presenting slides. That was the culmination of part 1 of our lecture. So we're going to go on to part 2 now. Again, work through these, make sure you have some idea what's going on. They're good study problems, and they're good ways to know whether you're actually understanding what the compiler is doing. The other thing that's good about these problems is you can type these into the interpreter, just like you do down in the window in the Spider, and it gives you practice in coding. One thing that I like to tell you guys is, you're learning a new language, and it's just like French or Spanish or Russian or Chinese or English. You need to practice it in order to get good at it. And all of these things we do, the lecture exercises, the labs, the homeworks, are intended to force you into practicing because it's really the only practical way to get to do it. So if you can get in the habit of pulling up the interpreter and just muddling around with anything that we introduce, you're not going to break anything. You can always stop your interpreter and restart it, and you're going to get a better feel for how things actually work. That's one of the reasons that up here we're asking you to kind of play with these. Play with the modulo function. Do something like on the spider window. I'll do one of them for you. I'll do the easy one. 8 modulo 3, right? That should give us the remainder when 8's divided by 3. That hopefully is going to be 2. And then 8 integer divide by 3 should be, the integer portion of 8 divided by 3. So that should also hopefully be 2. But see what happens when you do minus 3 and plus 3 and minus 8 and minus 8 and minus 3. And see if you can figure out the pattern. It's kind of fun. All right.